at the sun's rage breaking through the void. Silent in the cosmos, no sound to be destroyed. And new ways I catching fire's endless way. Numbers on a screen can't hold the burning day. Telescopes hunger feeding on the light, chasing the storm in the endless night. A flare of anger speeding through the black. We measure its fury but can't hold it back. How fast does the fire run, tearing through space? A question we whisper to the sun's fierce face. Data pours down like a digital stream, but we can't outpace the coronal dream.
So our first group, so this is the, I realize this is the 20th year of High Star. Yes. And so starting off, we have our solar group. Now I want to let you know that we think these are the first high school students that have used data from the Daniel K. Inouye Solar Telescope here on Maui. So very exciting. And our solar group team members are Sebastian Holtz-Perry. Is that right? Holtz-Perry? Yes. Sebastian is a rising senior at Seabury Hall, and this is his first year at High Star. James Anchetta is a rising junior at Baldwin High School. This is his third year at High Star. He's mostly done asteroids, but this year has branched out into he's seen the light, we'll say. No? Yes, okay. Here we go. Give him a round of applause.
Okay. Our project is mapping velocity structures in a solar prominence with DKIST and cryo-NIRS. And our mentor is Sage Constantino.
So, first of all, what is a prominence? A prominence is comprised of chromos... Oh. So, a prominence is comprised of chromospheric materials suspended in the lower regions of the solar corona. And a good example of this is right here. This is specifically the one that we are analyzing. And this was taken with the SDO Space Telescope on October 22nd, 2024.
This was also taken by the SDO telescope, and it is a raster, which is a square that'll be made up of many slit photographs that will cover the entire square so that we can map the particular part of the prominence that we want to view. As you can see, this is the square, and we take multiple raster photos. We took about 5 of the entire square a few times. We only used 1 for our presentation today.
So why is this important? Why should we study prominences? Well, since the sun is our star and it's a very close celestial object compared to others, it's important to study its solar activity because when that solar activity could hit Earth, it could have some devastating events. Like, for example, this happened a while back during the Carrington event. A solar flare hit the Earth and it caused massive destruction. There's also speculation that these solar prominences from the sun can have an effect on solar winds. And solar winds are important for space engineers because they need to know the space environment really well before they send like satellites or probes out into space.
Here is another photo of the solar prominence, which is more clear, and you can see its sort of colder looking color where it's darker, and how it seems suspended in the atmosphere of the sun. It is, see how it's curved sort of? So the front part of it would be the part that you'll see later is moving a little slower, and then the back of it will be moving faster, but you'll get to see that later.
So we use the Daniel K. Inouye Solar Telescope, or DKIST, imaging spectroscopy, and it's very accurate at measuring the Doppler velocity, which we'll get into later. It's capable of capturing the highest resolution currently available in the world. And we also use the SDO Space Telescope to get like a broader view of the sun, whereas DKIST was used to get the really fine and nitty-gritty details, to get those high resolution data that we need.
Okay, so we know the sun is made of helium-1 mostly. So we were able to get the lab data for helium-1 and make a predicted graph on the far right that would show the helium-1 as a graph. And then we got the actual data from the sun in our DKIST photos and used that to make an actual graph in the center. And that was very similar to our predicted graph because it is helium. So we decided that this was the best light to take the photo in, and best light spectrum, so that we would be able to see all the details best and make sure it was a very accurate photo.
So the way that we measure the velocity of these solar prominences is through Doppler shift. Doppler shift is a phenomenon where, as a source emitting waves moves closer to it or farther away from an observer, the waves are either contracted or stretched out. A good example of this in the real world is when a ambulance siren passes by you. As it comes closer, the waves compress, which then when it reaches you, the observer, the pitch of the siren is higher. And when it's moving away from you, the waves are kind of stretched out, which leads to a lower pitch. And applying this to prominences, this also happens with light waves. So when a prominence is moving closer to you from the observer, the light waves emitted are compressed, meaning that it'll look a little bluer. And if it moves away, then it'll look a little redder because the waves are stretched out. So seeing how blue it is or how red it is can show us how fast it's moving, either closer to us or further away from us.
Okay, in this graph, this is it's a velocity versus a brightness on the X and Y axis. So you can see on the right, it has the red dotted line, which is a Gaussian fit we predicted for the ideal shape of the graph. And that is used to go through all the photos we took, and we created a graph for all of them and determined this was the best graph that matched up best with our Gaussian fit, which is basically like a bell curve. And you can see at the top, that would be the bulk mass of the prominence, and that is how much of it is moving. Like the most of it is moving at a roughly 5 kilometers a second towards Earth. And you can see that drawn by the pink line there.
So this, our spectral image, it's a little, we illustrated it with blue on the left and red on the right to represent blue shift in the negative Doppler velocity, which means it's coming towards us, and red shift in the positive Doppler velocity means it's moving away from us. The figure on the right, measured by brightness over Doppler velocity, again, most of the material is here moving closer to us, meaning it's a little bluer. And this little movie on the right or left is all of the images taken by DKIST. And the one we used is the 34th step, which is the 34th, because the slit spectroscopy, the slit imaging, it moves up the raster, and this specific one matched up with the Gaussian curve the most.
Okay, so this is also step 34, and we were able to determine that it was like the best like the distinct Doppler shifted parcels. So you can see that half of it, roughly, is on one side of 0, which 0 represents like it's not moving. So on the left, it would be moving towards Earth, and on the right, it's moving away from Earth, and that's represented by blue and red. So then the most of the parcel is moving towards Earth at like 5 kilometers a second, as we said earlier. And there's a smaller part, but there is still some that is moving away from Earth at roughly like 26 kilometers a second. So then you can see that it's moving in 2 directions, and that it will have a sort of loop shape to it.
Okay. The here is a histogram with a bimodal distribution. We can see that again a bulk of the prominence material is moving slightly towards us, and bit of it, a bit of it. There's another spike here moving away from us. So this shows that there's a bit of material moving close to us and moving away from us, which is really interesting.
This is really interesting as well, because this is showing the entirety of the prominence, and it's showing that it has a sort of wave pattern to its velocity. So it's moving at different velocities throughout it. And we're assuming that this is one continuous prominence and there's no broken up parts of it. It's not being sheared by the gravitational thing, at least for this assumption. And so if it is truly like that, then this would be very interesting, because it is unusual, well, not unusual, but just we don't know how these create these sort of wave effects. So many scientists disagree on how it happens, but they do agree that it does happen. And so it would be very interesting if we could get more rasters and graphs about this to see if this is sheared or if this is one solid piece of the prominence that is moving in various velocities in this sort of wave motion.
So here, there are a few next steps we can take with this project. The first one would be to, again, with that wave motion, figure out what is causing that wave behavior on the Doppler shift graph, what is causing like that fluctuation in velocity. Another step would be analyzing more rasters on the sun to act as a follow-up to that prominence and follow it over time. And we could also take a triple Gaussian fit to make it more accurate, to make the graph fit more accurate.
Do you have any questions?
Questions?
Troy?
What was our favorite part of doing this project? I think the really cool part was using the DKIS data. It's not public information, or it's not public data. We're one of the first people to actually use this data and look at this really high resolution analysis of the sun prominences. So this is like, yeah, it's first time we've seen this kind of data, and I think that's really cool.
Yeah, I thought it was really interesting learning about the Doppler shift in this. It's very interesting, and how it's very useful for this type of project. Any other?
Look up to the sky, it's a cosmic dance. Big fat exoplanets in a solar romance, orbiting stars in a celestial trance. Mysteries so deep they don't stand a chance. Big fat exoplanets spinning so wide, hiding in the dark where the secrets reside. Galaxies are watching, they can't be denied. Big fat exoplanets on a stellar ride. Blinged out in the night, color so vivid, it's a galactic delight. Gas giants flexing with a glow so bright, rocky world spinning in a gravitational fight. Big fat exoplanets spinning so wide, hiding in the dark where the secrets reside. Galaxies are watching, they can't be denied. Big fat exoplanets on a stellar ride. They got rings like kings blinged out in the night, color so vivid, it's a galactic delight. Gas giants flexing with a glow so bright, rocky world spinning in the gravitational fight. Big fat exoplanets spinning so wide, hiding in the dark where the secrets reside. Galaxies are watching, they can't be denied. Big fat exoplanets on a stellar ride.
Ladies and gentlemen, this is our exoplanet group. Actually, I wanted to make one comment. One other thing I should have mentioned with the solar group is that the mentor was a former High Star student. And so it's sort of, and he's now in grad school. It's a little bit like having, a family member coming back home. So we really appreciate Sage being joining us this year. The exoplanet group. Solar group, exoplanet group. Yes, here we go. The students are, Emma Kalikal. Emma is a second-year student at High Star. She's a rising sophomore at Baldwin. And she's been working with the program for a long time. For several years before that, we've been working on various science projects for I don't know how many years. We won't tell them. All right? But several years. Anna Carta Murley? No. Try it again. Say it. Anna Carta Murley. So I was pretty close. Okay. Anna Carta Murley is a first-year attendee of High Star. She's a rising 8th grader at Montessori School of Maui. Mila Jasovich, there's no K in there. Mila Jasovich is a rising 8th grader at St. Anthony's. And they will be discussing exoplanets, discovering new worlds, and I will let you introduce your...
So, Exoplanets by
Emma Kalikal,
Anna Kartamerli and Mila Jasovich, and our mentor is Ray Ali. What is an exoplanet? Extrasolar planets, or exoplanets, are planets found outside of our solar system. Why do people study exoplanets? People like to learn about exoplanets because we want to find signs of life outside of our solar system.
a graph that is showing everybody how many exoplanets have been confirmed. So there have been around 5,910 exoplanets that have been currently confirmed to orbit stars, and they're sorted by how big they are, how they compare to other planets in our solar system, and their orbital configuration.
How are these exoplanets different? Most of them are hotter and larger than our solar system planets. Kelt 9b is a super hot exoplanet, so hot it vaporizes metal. There's a planet called WASP 76b where it rains molten iron. Kepler 22b is the first exoplanet to orbit within the habitable zone of the Sun like star, which means that liquid water could potentially live on the surface.
How do we find exoplanets? One way of finding exoplanets is by using the transit method. That is when a planet passes directly between an observer and the star it orbits. It blocks some of that starlight, causing a slight dimming of the star's light. Another way is by using the Doppler method. This is when we look for a star's motion caused by the gravitational pull of planets around it.
The TESS telescope, or the Transiting Exoplanet Survey Satellite, is a space telescope designed by NASA made to study life outside of our solar system using the transit method. That is when you observe the dips of light in the star, which could potentially mean a planet is possibly passing by.
Our research process. First, we find the stellar light curve, remove stellar variability, search for periodic signals in the light curve, stack the data over the periodic signal, and fit the shape of the planet transit. But if you don't understand, don't worry, because Emma will go more in depth.
So basically, this is the basis of the transit method. It's called a light curve. What it does, it measures a star's brightness over a certain period of time. Usually, when a light curve is good, it should just be a straight line because the star's light won't change because it's a star. But as you can see here, it's kind of weird. It's really wonky, and that can happen for a multitude of reasons. It could be star quakes, prominences, or even spots that make it thinner. But the main one that we're looking for is a transit signal, basically when a planet goes into transit. But it's kind of hard to detect with all this noise, right? So what we need to do is model out the stars, the stellar activity. Basically, we take all of this wonky data over here, and we average it out and flatten it, as you can see on this table. Basically, flattening it helps us find where the transit signals are. And as you can see here, they're much easier to detect. But we don't know the orbital period, and that's pretty important because we need to be able to catch the exoplanet. So we use a periodogram. A periodogram basically tells us if an event is happening over a specific period of time. So as you can see here, around the 4.5 day mark, some event keeps happening over and over and over again. And when we check it using the light curve, we can find out if the planet is orbiting. As you can see here, it is confirmed every 4 days we mapped out each of the transit signals. Now this is good and all, but to get a clear view of the exoplanet, we can fold this on top of each other to create this transit signal right here. And this transit signal, you can learn a lot about the exoplanet using this. For example, as you can see, the dip is really big, meaning the exoplanet is also really, really big. And also, the gap of the transit is super not wide, meaning that the planet is orbiting it at a really fast pace. Now, if you really wanted an even clearer version of the transit signal, what we did on this one is we zoomed into this little spot over here and essentially mapped out clear how deep the dip was and how wide it is. The candidate that I've been showing you is TOI 219, and it's super cool because its radius is about 2 Jupiters. It is even more cool considering its orbital period is 4 days, which means it could be super close to its host star. Yeah. But enough about that. My partners have also found some pretty cool connections, and I'm going to hand it over to them to show you guys what they have found.
New exoplanet candidates. Alright.
The star is named TOI 6656, and the planet name is TOI 6656.01. The orbital period is about 0.82 days, or about 18. So this is the star's brightness over time. These gaps over here are where the telescope wasn't looking at the star and wasn't collecting data. And these little line type things are the star's brightness over. This is the periodic signals in the light curve. So as you can see right here, there is a significant change, and it happens here because the orbital period is about 0.82 days, and this change happens a little bit after 0.8. And this is the transit stacked signal. Here, every 0.8 days, we cut a piece of the light curve and stacked it as seen on this graph, so we can see the transit signal a little bit.
So our next step in this project to continue our research would be to use the Las Cumbres Observatory Network to get more info on each of these exoplanets. We want this because even though we have some pretty clear-cut evidence, we just want some more extra clarification, and some ground-based photometry would be really good in confirming that there are indeed exoplanets like stars. Any questions? So life hasn't been confirmed on exoplanets yet, but with the right um, conditions, it could be possible. Yes. Were you raising your hand? The ones, essentially the ones in motion. So we were interested in these exoplanet candidates because for me personally, mine is really cool because it's a really big planet that's orbiting. It's a really big planet that's really close to its host star, so it could be like Jupiter, but really, really hot.
And then for me, I found my planet pretty cool because it was pretty cool that the orbital period was only 18 hours. So, which, like, for Earth, it's like 365 days. And yeah.
Gazing up at the sky so fast, questions burning like a rocket blast. Twinkling lights in a cosmic sea. How old are you? What secrets do you keep from me? Born in a swirl of stardust bright, a billion years or just last night. Do you whisper tales of time gone by, or keep your age locked in the sky? Oh, star cluster, shine your glow. Tell me stories I don't know. Ancient wonders blazing high. How old are you in the endless sky? Galaxies spin in a cosmic dance. Your shimmering lights put me in a trance. Are you young or weathered by time? Still you sparkle like you're in your prime. Astrophysicists can take a guess, but you keep secrets under your dress. Timeless beauty scattered wide in the heavens where you reside. Oh, star cluster, shine your glow. Tell me stories I don't know. Ancient wonders blazing high. How old are you in the endless sky? Born in a swirl of stardust bright, a billion years or just last night. Do you whisper tales of time gone by, or keep your age locked in the sky? Oh, star cluster, shine your glow. Tell me stories I don't know. Ancient wonders blazing high. How old are you in the endless sky?
All right, ladies and gentlemen, this is our STARS group. And Rena Mae Lana is a rising sophomore at Baldwin High School. This is her third year at High Star. She's worked with binary stars and then galaxies, and now she's working with star clusters. So she's kind of going around the sizes of stars to see which size she likes, I think. Okay, and Linjel Pagel is a second-year student at High Star, a rising sophomore at Baldwin High School. Her previous interests also include galaxies. We wanted to introduce Anthony Phillips, who unfortunately was not able to join us. He was part of the group. Anthony is a rising 8th grader at the Montessori School of Maui, and their mentor is Fede Kiti. And I will turn that time over to you. There we go.
I'm Raina.
And I'm Linjel.
And today we're going to be explaining or showing you the ages of our stars. So stellar cluster. So why do we care about stellar ages? Finding stellar ages can help us get a better understanding on the past of our universe and our galaxy, especially ours, the Milky Way. So, what is a stellar cluster exactly? A stellar cluster is a group of stars that were born at around the same time, have the same distance, and move together in space. So, how did we find the cluster? Well, our first step was to receive the data by using Gaia for our cluster, NGC 2516.
We
Now-
chose NGC 2516 specifically because there have been literatures about the age being unknown for this specific star cluster, so that's why we chose it.
And the second step that we did was to look for the size of the cluster and coordinates using SIMBAD. And our third was to apply our two filters, parallax and proper motion, to identify the stars that are in the cluster. Now, our first filter is parallax. What is parallax? Parallax is basically the distance of the stars. Now, in this graph right here, we have the x-axis as parallax, milliarcseconds, and the number of stars. The blue bars right there are just all of the stars out of our cluster, and the red bars is basically our cluster of stars, as you can see in the red. Okay. Our second filter is proper motion. What is proper motion? Proper motion is the motion of stars in the sky along the right ascension and declination. As you can see in our graph right here, our x-axis has proper motion in right ascension, milliseconds per year, and in our y-axis, we have proper motion in declination, milliarc seconds per year. And, well, all of the blue dots is basically just the outer field of our cluster, and the red dots is our actual cluster that we found.
Alright, so now that we have applied both our two filters, you may think, oh, I think it's time for us to start estimating the age of our cluster. Well, we're not really that close yet, as we also have another problem to deal with, which is interstellar extinction. Now, what exactly is interstellar extinction? Well, imagine it like this. Hold this. Imagine this. This is us. We are the observers, and this right here is our cluster. In between us and the cluster are these dust particles, and as our star cluster emits this stellar light, these dust particles absorb this light and scatter it into blue light. This causes the cluster to appear redder and fainter.
So think of it this way. When we put on our sunglasses in a sunny day, when we put on our sunglasses out on a sunny day, the light becomes dimmer and the goes darker. That's basically it. So the dust particles absorb the light from the stars.
And now that we have corrected the extinction, we now have this graph. So, after removing the extinction, this causes the cluster to appear more bluer and brighter. As you can see here, this is the graph that we have now. Your x-axis represents your color, with your left representing the bluer side, and it's hotter on that side as well. And your right side, which represents the redder stars, and these redder stars are cooler. Your y-axis represents the G magnitude, and it's in G because this is the G band, and we are using it because, well, it's Gaia. This is the Gaia data. These stars over here, there are two colors. We have the orange, which is the stars when they were not corrected, and the blue are, well, the extinction, like when it's removed. And as you can see here, there is a slight shift to the left because after undoing the dust particle effect, we now can see that they are actually brighter and bluer as well. And you might think that this is probably the first time you've seen a graph like this, but you're also wrong too. As you can see here, if you remember this graph right here, this is the HR? Yeah, this is the HR diagram that, if you remember Dr. Van Sater's explaining, this is the same graph as our graph right here. There's a notice the main sequence right here, as well as also a noticeable main sequence on our diagram as well. And in this graph, your x-axis represents, what was it again? This was the
Determines the
temperature, and the y-axis represents luminosity. The only difference between these two graphs is that they both go under different names, but they are still the same. All right, now that you know, now that we have removed the extinction, it's now time for us to calculate or make an estimate on the age of our cluster. And to do this, we use isochrones. But what are isochrones exactly? Isochrones are stellar models that are used to show the evolution of stars. Take the word isochrone, and it's made of two Greek words. Iso meaning same, and chron meaning time. So basically, this model consists of stars that are the same age, but they have different masses. As you can see here, this is also an HR diagram, and I think I should close it here. Yeah, this is also an HR diagram, and your x-axis represents the surface temperature, and your y-axis represents luminosity. These colorful lines that you see here are the isochrones, with the blue isochrone representing 5 million years, the yellow one representing 20 million years, etc., etc. These isochrones, they have the specific...
Yeah, they have time periods that go.
Yes, and and they go up as
Basically, what this is the 5 million years. Well, it kind of just tells us how long the star is going to live, etc. During like I guess different time periods. And each of these, and then these kind of go slower. Not in
goes down. An example of how we apply the isochrone to our data is if we placed a point, which is a star, if we place a point on one of these lines, this means that this star is that age. So if we put a point on the 5 million year isochrone, this means that the star is basically 5 million years old. Now that you know what isochrones are, it's time to apply it to our data. So this graph right here is the graph that we have now after applying isochrones. And we got the isochrones by downloading it from the
Padova
database and applying it to our data. Our main goal over here with isochrones is to find the isochrone that best matches the cluster data. In particular, we want to look at the main sequence turnoff point, which is right there.
Okay, so basically the main sequence turnoff point is the main sequence turnoff point is basically where the stars lose hydrogen, lose their hydrogen fuel, and so they kind of like just go down. And so as you can see, the main sequence turnoff point goes down by like a few decades. Well, actually not decades, sorry. A few million years, because that's like how long it takes for them to get their hydrogen fuel out of their system.
With this in mind, if you look right over there, closely over here, this is where we're looking at, and if you can see here, there's 250 million years isn't really the isochrone for our star cluster, but if you look closer here, the cluster appears to be more in the range of 150 to 100 to 150 million years. So with that in mind, we can say that our star cluster is around 100 to 150 million years old. And what can we conclude from this? Well, we can conclude and say that our star cluster is pretty young. If we decided to compare this to our sun, which is 4.5 billion years old, this star cluster doesn't come close to how old our sun really is.
Oh, another thing we can conclude is that we're probably going to write this in a paper and also put it in science fair. That's our plan. Yeah, thank you. Science fair.
Whoa! Any questions?
Any questions?
Oh. Oh, I think we could maybe observe more star clusters.
Yeah, we could
inside.
observe more star clusters that don't have an estimate of an age. So, any more questions?
There's usually thousands and thousands upon thousands of stars in a star cluster. Usually.
Yes.
You're how stars are, like the star clusters are formed?
I'm sorry, could you repeat your question, please?
Yeah.
So you're asking how and why these star clusters are kind of like bundled up together. Oh.
At the moment right now, we're not sure, but we'll get to you later with an answer for that question. Sorry.
Yeah.
We're willing to answer.
Stars that burn so
Yeah.
bright in cosmic winds, they light the night.
All right, thank you.
Tight by ear, it's pure
Great.
night. Two white dwarfs dance, then
And
take flight.
our final group is the Supernova group.
Supernova sparks, let's watch it glow. Every type it's still to know. Exploding hearts, the skies bestow.
We will ask them to come up.
Massive might. A dying star's dramatic fight. Its core collapses, out it blows. A nebula forms where it used to pose. Neutron stars and black holes form. From chaos comes a cosmic norm. These remnants whisper through the void. Creation birth where stars destroy. Boom, boom, boom goes the stellar show. Supernova sparks, let's watch it glow. Every type it's still to know. Exploding hearts, the skies bestow. Tight even dikes are rare delights. Stripped of layers and stellar heights. No hydrogen left, but they still ignite. Their fireworks dazzle the endless night.
Okay. Ladies and gentlemen, our final group is the Supernova group. The Supernova group is, so we're going out with a bang. Okay, so the first member of our Supernova group is Chelsea Miguel. Chelsea is a second-year student at High Star, and last year she worked on exoplanets. So you see there's some migration from exoplanets to galaxies and back. She's a rising sophomore at King Kekaulike, and she also has some interest in biology. Troy Carlson is a second-year student at High Star. Last year he was working on exoplanets, and he's a rising software at King Kekaulike. Also has a lot of interest in robotics. Lexi Lombardi is a second-year student at High Star. She's a rising sophomore at King Kekaulike, and last year she did some work on asteroids. She actually is working on a circular that she will be publishing on an asteroid that she's been studying. And then Viola Stevens is a first-year student here at High Star and a rising freshman at King Kekaulike. And oh my gosh, what? Did I get something wrong? What? Viola. Yes, did I say that wrong? Viola Stevens, okay, is a first-year student at High Star, rising freshman at King Kekaulike, and believes that purple's not a real color. Look that one up. The work they're working on today, of course, is Supernova, and I will let them go ahead and take it from there.
This is Supernovas by Lexi, Troy, Viola, and Chelsea. First of all, what are supernovas? Supernovas are the big light and bright explosions that a star occurs during its final moments. And what did we do? What we went to was Transient Name Server, which was a catalog of unclassified and classified supernovas that we could study, and it proved really useful. We looked at the spectras. Okay. We looked and analyzed their spectras, and our mentor helped us calculate redshifts and helped us learn more about supernovas. So first of all, how do we classify supernovas itself? Well, we use a spectroscopic approach on this. And we use the spectra. Spectra is basically a graph on the intensity of light um, through wavelengths. Through we calculate it by angstroms. So the main classification on supernovas, if if they're a type 1 or a type 2, is based on hydrogen. On the spectral line, if there's a presence of hydrogen, then it becomes a type 2 supernova. If there's an absence of hydrogen, then it's going to be a type 1 supernova. And it's going to be an emission line. So it's going to basically go dip up on the spectrograph itself. On the sub-classifications of type 1 supernovas, we search for the silicon absorption line at 6,656, which is basically a dip down. So if there is a silicon emission feature, then we classify it as a type 1A. If there isn't, we search for a helium emission and absorption line, because helium is a really distinct element itself, and if there's no presence at all, then we classify it as a type 1C supernova. And if there is, then it's going to be classified as a type 1B. Moving on to the subclassifications of type 2 supernovas, we have type 2b, type 2l, and type 2p. Type 2b is mostly differentiated by type 2l and type 2p. Type 2 is, what I learned, is pretty wimpy and has little hydrogen left. But what makes these two type 2l and type 2p very similar is the light curve shape. The light curve for type 2l means type 2 linear. The light curve is really linear. It's like a parabola. And for the radioactive decay as well, it's linear as well. It decays into cobalt without anything, without a without a constant light in the middle. And we have type 2 Potal, which is kind of different than linear. A Potal is basically the parabola, but there's a stagnated constant line across, and then it swerves down. So the Potal is from what the graph is saying. It shows that the supernova has a little bit of light left, and what the Potal means is that means there's a H recombination. An H recombination is basically the hydrogen ionizing and giving off photons again, which allows the supernova to maintain its brightness for a short period of course before it dies out. And then we have some exotic ones that we won't really talk about, like hypernovae, that will be researched more into the future. And I'll leave it to Viola.
Thank you, Chelsea. So what we have here is a young galaxy, or they are also called spiral galaxies. And the type of supernovae that we find in spiral galaxies are type 2, type 1b, and type 1c. Then next we have old galaxies, and old galaxies are called elliptical galaxies. And the type of supernovae that you will find in old galaxies are type 1a. And Troy will talk to you more about these types of supernovas.
So, I'm going to be talking about the progenitors of all the types that Viola was talking about. So I'm going to focus on the type 1As first. There are two scenarios that it can go down. It can go down either the single degenerate path, where it gets paired with the main sequence star, and the white dwarf star will slowly steal material from it, and eventually it will gain too much mass and it cannot support its own weight. It'll explode. It'll have a thermonuclear explosion. The other scenario is a double degenerate scenario. What happens is there's two white dwarfs in this scenario instead of a main sequence star.
what happens is they orbit each other slowly, and eventually, over time, they will either collide or merge. And in this event, they will end in a thermonuclear explosion. Now on to the Type 2, 1b, and 1c. The Type 2, 1b, and 1c, they all come from the massive stars. What happens is they all have a fuel source. Eventually, they will go through their cycle, and they come to iron. Iron is a problem because it can't be used in fusion to create energy. So over time, it just creates a iron core, which cannot be used for fuel. It creates too much weight for it, and like the Type 1a, it will explode over the weight. The difference between the Type 2, 1b, and 1c's are that the Type 2s, they retain their hydrogen outer shell, and they also retain their helium outer shell. Where the Type 1b's, they lose their hydrogen shell, but they continue to have their helium shell. Where on the Type 1c, they don't have either of their outer shells. And it can be seen in this diagram. We have the Type 2, the Type 1b, and the Type 1c.
So next up, we're going to have some of our graphs, which is mostly the bulk of our project, because our goal of our project was to identify some supernovae and classify some supernovae that have never been discovered before. So in this first graph, this is actually a classified supernova, and when you're identifying supernovas, it's a little bit of a learning curve because there's a lot of things that have to come into account. You have to take into account when you're looking at these. One of the first things is learning all this different terminology. So on our x-axis, we basically just have wavelength, and it's measured in angstroms, which is just a scientific unit. And then on your y-axis, you just basically have essentially how bright it is. And on the left side, you're going to hear me say that it's more on the blue side of the graph, which is the left side, or the red side of the graph, which is more on the red side. And one of our first things we would do when we were looking at this is we would use the chart that Chelsea pointed out earlier, the flow chart, to help us identify, since we know one of the main elements in some supernovae is helium. Here we looked at it, and it actually had helium, which is a good sign, because it meant that it was a Type 2 supernova. And Type 2 supernovae are also typically on the more blue side of the spectrum, meaning they're hotter and they're also typically more intense. Moving on to when we had some newer ones, these actually, the next 4 graphs you'll see are brand new supernovae that were identified in about 3 days ago. So right at the start of High Star. And this was actually obtained by our mentor. He stayed up all night slaving away on the UH-88-inch telescope. But yeah, so these are our graphs that we obtained that he got for us, thankfully. And our first step would be to look at hydrogen. And if you were to look at just hydrogen, this is blue lines actually represents hydrogen, which typically spikes at around 6,500 as its strongest line of emission. But an emission is basically a fancy way of saying that the supernova is giving this out, and that's kind of these peaks you'll see. Let's see if I can find any absorption in this graph. Here's a good example of absorption, and it's basically when you see dips, which means that the supernova is kind of taking in this wavelength. And this, we can see a strong absorption line. And if we were to look at this right now, we would think, oh, it has helium, right? So that must mean it's a Type 2. But that's not true, because there's this little thing called redshift and blueshift. And basically what redshift is, it's when something's moving further away from us, so its wavelengths are getting longer, shifting it more towards this side of the graph, the red side. And then essentially the exact opposite for blue shift, so it's going to shift it more to the left side of the graph, making it appear more blue. And we actually did calculations on the redshift, and we did the calculations on the redshift for this one. This graph doesn't have redshift accounted for it. But this is actually not a line of helium, so we determined that it was a Type 1a because it also had silicon. There's a spike of silicon in there. Moving on to our next graph. This is, again, unclassified one. And this one's really interesting because we see this really strong line of helium. Even taking into the redshift account here, it would still be pretty close to helium. But we see this spike of helium, but it's not actually, we don't think it's from supernova because it's it's a really strong line of helium that we're seeing, but it's extremely narrow, which typically isn't emitted by supernova. Typically, they have more of a spread out spectrum right here with helium, and we know that galaxies often produce a lot of helium since it's one of the primary components in most stars. So we assume this is from the galaxy, and when you actually look at the image from the Transit Name Server, which is a program we use, it's actually close to the center of a galaxy, which would explain this spike. So due to this, and we aren't really getting a really good signal to noise here, it's really hard to tell what type of supernova this is, so we were unable to identify it. The next one is actually a pretty graph we're seeing here. We're seeing no lines of hydrogen, but we are seeing silicon, which is really good, which again means it's a type 1A. And moving on to moving on to our final one, it's really similar to our last one, but one big difference in this graph is that it has calcium over here, which we're seeing being strongly absorbed by the supernova. And this one's also much brighter than the last one. That's another big key difference, because it's more intense and brighter. So overall, in conclusion, we were able to look at a bunch of different types of supernovae. We were able to look at a bunch of different types. Even when we were learning, it was really fun to look at these. And when we were able to when we were actually able to take these for our own selves, we were able to correctly identify 3 out of the 4. We think it's a really strong possibility that these are all type 1A supernova, which also would make sense because most types of supernovas, type 1A is a pretty common type, and also they're a very bright type, which would explain why we're seeing so many of them. And I can't speak for my partners, but I thought this project was really, really fun to do. You guys agree with that? Yeah, it was really fun to do, and I overall had a really good time. Thanks. Are there any questions?
It's the man in the back.
So the question was if there's a way to know what kind of supernova our sun will be. And I suppose we do know some of what the sun is made out of. We know it's made out of hydrogen. So that would mean it would probably follow towards the type 2 supernova. One of those is probably my best guess. Yeah, type 2. So, and then after, we'll never get to see it after, but without anything else really off the top of my head, I think it would be some type of type 2.
Any other questions? Yes, some I'd say today I'm feeling kind of like a. Oh, so the question was, what kind of supernova are you feeling like? Today I'm feeling kind of like a type 1B.
Feeling sort of rare today. I'm feeling really empty. I'm feeling like a 1D.
I'm feeling kind of bright today, so I'm feeling like a type 1A. So.
Feeling a little special today, so I'm kind of feeling like a type 1B.
So our mentor is Willem in the back.
Yeah.
Or Vector.
He is probably a type 2P, my guess.
All right. Well, thank you, everyone. I wanted to say thank you to all of the mentors. Can we get you all to stand up? Give them a round of applause. The mentors. Here and here. Carolyn Kiichi, we want to thank Maui College for hosting us. We also want to thank Los Cumbres Observatories and Air Force Research Labs / Space Force for sponsoring the program. And thank you all for coming, of course. Have a good evening.